All right. Well, I've got a couple of PowerPoint slide things to show you here in this class just because operational technology was unfamiliar to me. I actually used this book called Operational Technology, The Beginner's Guide by Bickerstaff, but I don't recommend it. It wasn't a very good book. And after I taught it once using that book, I discovered that there is a much superior free PDF from the government, the NIST PDF, that really goes through securing operational technology very well. Uh, so this is what I'm going to use for a textbook in the future. But as just an orientation for people new to operational technology, I found the first couple chapters of this book to be pretty good. And these slides, by the way, for what they're worth, they're on this page. You'll find them here. A couple lectures up there if you want them. But I'll just talk about this stuff. So operational technology is technology for things like industrial equipment. It interacts with the physical world for manufacturing, energy, healthcare, and so on. And so there's the topics here. Differentiating OT from IT is the main thing here, and the Purdue model, which was new to me. So OT is concerned with physical processes like manufacturing and power generation, driving machinery, controlling pressure and temperature and such, as opposed to IT, which I think we're all more familiar with, computers, networks, systems for processing data. And so OT is on the plant floor, and it's using equipment that's mainly intended for reliability, and it's going to be used for probably decades with very little upgrade, whereas IT is, of course, our traditional operating systems where we expect everything to go to another version every couple of years. And that's the fundamental problem. And now, in the old days, the OT would just not be connected to the internet or the other system at all. It would just be equipment that you control by physically being in the room. But now, by converging the two, you have huge advantages. You can now remotely control your OT systems, remotely monitor them, and all that. So it has great advantages for your manufacturing. The problem is it also exposes them to cybersecurity risks. And the OT equipment was never designed to handle modern cybersecurity risks. And in IT, as you know, we have confidentiality, integrity, and availability. That's security for an IT system. But for an OT system, it's safety, reliability, and productivity. It just has to work and be reliable. And cyber threats, so that like viruses and remote hackers, are just not something that was considered in the design of these things. So they have a network infrastructure for the OT system. You got hardware and software, but your hardware is things like sensors and actuators, physically changing equipment, and your network is typically small and localized for the OT part in one room or one building. So you got strange OT protocols like Modbus, Profibus, DNP3, and unfortunately, a whole lot of this operational technology stuff uses proprietary protocols from the manufacturers, and there is no free version and no free emulator. So I can't give hands-on projects for a lot of those, but the few of the open source ones, I can give you hands-on projects, and that's what we're going to use as primarily Modbus in the hands-on projects. And so as they connect, of course, you get advantages of being able to use IT processes like enterprise resource planning and databases and such, but that means you expose your OT systems to attacks. So the OT network architecture is hierarchical with a variety of layers, and you got to consider determinism, where you know what time things will happen, the latency between instructions and the activity, and jitter. All these things may be more important for your OT systems than they are for IT systems. And here's the Purdue Reference Architecture, which is essentially the OSI model for operational technology, although it is a whole lot less fixed and uniform. I've seen several different versions of it, but you have low levels with batch, continuous, and discrete control, and then you have level 3 with manufacturing operations and control, and then business planning and logistics above that. So this is, as much as anything is organized, this is the general organizing structure of your OT networks. And then you have the protocols, Modbus, Profibus, and DNP3. These things are very lightweight, simplistic, typically no encryption, often no authentication. They're intended to connect devices, but they're like the really old internet protocols like Telnet and FTP back in the days when nobody thought about security. So Modbus is really old, from 79, very common, almost universal. Profibus is a little more complex, and DNP3 is the most robust, common in utilities, especially electric utilities, commonly used. So the network architecture, at the top level, you have enterprise systems, a data analysis, process optimization, and oversight of the entire operation. Here you have control systems, and down here are the sensors and actuators at the low level that directly interact with the equipment. So you mentioned the OT network requires real-time control with defined latency and jitter controlled. And what you want is you want it to operate in a harsh environment, and you plan for contingencies like electromagnetic interference, failure, physical tampering, and so on. Those are your concerns here. And so you have redundancy and diversity, just like you have in IT systems, failover systems, and different components of different types. So one can take over if the other fails. And so it automates production. And you may now these days include some degree of artificial intelligence and machine learning. And so in energy, these are things we talked about. Energy, you may control turbine blades in a wind farm, control things in a nuclear plant, control traffic management, and so on. All this critical infrastructure, which is spectacularly vulnerable, and as we've all been hearing about, is all hacked by the Chinese like crazy and other threat actors, getting in our telco systems and in our power generation and water plants. And as far as I know, the only defense we have in practice is mutually assured destruction. We're all in all their stuff too, because securing all this stuff is going to take a long time to upgrade these old systems. And of course, it's in oil and gas and healthcare. So that's just a bit of orientation. And let me talk a bit about the second one too here. And then we'll get into the hands-on projects. So here's your key components. You have sensors that monitor things like temperature and pressure, actuators that carry out physical actions like opening a valve, PLCs, programmable logic controllers, that connect to the sensors and send commands back to the actuators, and then all the normal networking equipment above that, like routers, switches, cables, servers, and such. So you got operating systems, applications, and firmware. And SCADA systems are the high-level control system. And then you have distributed control systems that can move across a large facility to distribute control functions, so they're not all controlled from just one place. And so here's the hierarchy. At the top, you have enterprise resource planning, then SCADA systems, and then the middle layers contain PLCs or DCS systems, and at the lowest level are the actual field devices controlling the equipment. So that's the Purdue model. We talked about it. The top level is the most familiar from IT workers, with things like incident response and compliance, which we'll get to later today and all day tomorrow. Then you have your enterprise business systems, the demilitarized zone connecting the internal and the external network, which is where you really can put in much of the security that you're going to have. And then the lower level stuff, which is the OT stuff, the site manufacturing operation, the supervisory layer, the controller layer, and then the physical layer with its sensors and actuators that drive the systems. So everything is modularized, of course, like we're all used to. Different module devices replace each other, and that makes it cost effective. And supposedly, the system is deterministic. If the same condition repeats, the same action will result. That's the idea. A highly deterministic system, however, can be less flexible, so there's a bit of a conflict there between two desirable goals. And you want resiliency, which we've talked about, and you want security. In the IT side, that's confidentiality, integrity, and availability. And so the key, as now there was a time, an innocent time before 2010, before it became common knowledge that China was hacking all of our systems, when people imagined that they could protect IT systems with preventive measures. You'd have things like firewalls, intrusion detection systems, and so on the edge of the network, and you would say everything inside my network is trusted and clean. Now we can't have that anymore. We know that no matter what you have, people are getting through your defenses, their penetration inside. And so you have to move to a zero trust model where you assume that some of the systems inside your network have been compromised and you regard everything with suspicion. Um, and therefore, you have to have detection, network security monitoring to see if bad things are happening in your system. And you have to have incident response to respond to bad things you find happening inside your system, since you can't trust your defense measures to keep it clean in there. So this is the modern world we're all living in. All right. And so we talked about these protocols before. Modbus is probably the main one directly relevant to us. And of course, at the higher level, you've got Ethernet. IP is another one. And Profinet is an expansion of these. So that's a general orientation of the layout here. Let me stop this recording.